Hello, hello. Hello. Am I still muted? Hello, hello, hello. How are you? Awesome. Okay, cool. Yeah, I can hear myself too. Should I restart? I can restart since we're not that far into it. Okay, I will restart. Now you get to hear everything again. Hi, welcome to the workshop Reversing Rust Binaries, One Step Beyond Strings. I'm Cindy Xiao. My pronouns are she, her, or they, them. And I'm a senior security researcher at CrowdStrike and also a malware reverse engineer. So we'll give this introduction again. Are you a seasoned reverse engineer, but you tremble when a Rust binary lands on your desk? When you encounter a Rust binary, do you just run strings on it and hope for the best? So that is what I do. From talking to colleagues and from talking to other people who are reversers outside my company as well, that's kind of where we're all at with Rust reversing across the board. I primarily reverse malware, so I'm looking for indicators of compromise, things like domains or URLs, and all of us just run strings and hope a URL falls out, and if there is no URL, we don't really know what to do at that point. So the pitch for this workshop was, let's go just one step beyond running strings. Strings is actually like the best RE tool ever, right? It can be surprisingly useful. So let's use that as an approachable starting point for doing Rust reversing. If we're dumping strings from our binary already because we're looking for something, what do some of those other strings that we're seeing actually mean, right? What can they tell us about Rust itself, the language, and what can they tell us about the person who wrote the binary, and can we use that in any helpful way to guide our reversing? So today we're going to do a few things. We're going to build a working Rust downloader. So it's a very simple program that just downloads and runs a shell script. It is benign, I promise. We're going to learn about the string metadata that appears inside our downloader once we've built it. So we'll build it and we'll reverse it a little bit. We're going to actually use strings as well to find the entry point of our downloader, because that's something that currently the main disassemblers and decompilers that are out there don't really do for Rust binaries yet. And we're going to know where to find more information about the Rust runtime, the Rust standard library, and the Rust third-party library ecosystem, all of which are things we'll learn about today. Okay, so I will show this slide here, which contains a nice link to my GitHub repository where I have the pre-workshop setup instructions. I'm showing it to you now because there is an optional pre-built VM which you can download. It is a 15 gigabyte download, so I'm showing you now at like the beginning of the workshop so that you can like click the link and download it in case you need to get set up. But there's more detailed instructions there. If you go to github.com/cxiao, which is my GitHub profile, it is also one of the pinned repositories there. So you can go and take a look at that. But in general, I know people like their own reversing setups. So in general, you really only need three things. You need a copy of the Rust toolchain. So all of the tools that developers will normally use to build Rust binaries. Your disassembler or decompiler of choice, and an internet connection, because we'll need that both to pull dependencies for the Rust binary, but also for your shell script, that downloader thing. So I will leave it up for another second. And for the next 10 minutes, I will be talking about like background and motivation for the talk. So if you do not care about that, you can like do the setup in the background. There is some time. Okay. All right, moving on to the next slide. Okay, so now is where I actually talk about like my background, what I do, etc. But I want to talk about this because maybe it will help you understand some of my approach to this talk and how this talk is laid out. So currently I do malware analysis and reverse engineering, primarily for cyber threat intelligence reporting. here at CrowdStrike. I used to be a C and C++ developer before doing malware RE. So I'm often interested in like approaching things from the developer's perspective as well. Why did they choose this programming language? What does their source code look like? How easy is it for them to set up their tool chain? And finally, practically, we were just like seeing more Rust malware in our analysis queue at work. I'm on a team that's not really focused on tracking any specific adversary or any specific campaign. We do like general RE for a variety of internal and external customers. So I like to think we have a pretty good view of like the cyber threat landscape across the board, and we were just seeing more Rust, and we needed skills to deal with them. It got interested in this last year. This is a photo of me at Recon last year doing a lightning talk about Rust in the Windows kernel, which you might have heard about in the news. So thanks, Sergey, for the pic as well. Okay, so let's lay out some basic information about Rust as well, just so we're all on the same page about this language, because it is like very hyped nowadays. Like everybody wants to rewrite everything in Rust, right? So let's have some like actual facts about it. It's really meant to fill the same niche in terms of programming languages as C or C++. So systems programming language, high performance, and low overhead. What's unique about it, and one of the reasons that it is gaining a lot of popularity and attention, is that it gives you the promise of automatic memory management, but without the overhead of garbage collection. So if you're like not interested in comparing programming languages as a hobby, you might be like, what does this even mean? So we can contrast it with some languages that you might know about. So in C or C++, the programmer has to do a lot of manual management of memory. You do have to be thinking about allocations, deallocations, tracking things that references points to, etc. C++ gives you some tools to deal with this, but it's not perfect, and it's still possible to make memory corruption mistakes. With other languages like C# or Java or Golang, those will automatically manage memory for you for the most part by running a garbage collector at runtime alongside your program. So Rust kind of promises to be different from both of those things, the best of both worlds in some sense. And Rust has a mature open source library ecosystem now. It's been around for a number of years. And if you want to build a web server in Rust, if you want to write an embedded OS in Rust, there are quite mature libraries to help you do all of those things now. And finally, and I think this is a point that's maybe the most important, especially for like the malware ecosystem, is that now there's significant investments in support and funding from major software vendors like Microsoft in the Windows kernel. So we all love Venn diagrams. So this is a Venn diagram. So this is kind of what I talked about in the previous slide, where we have languages that have a really minimal runtime overhead and that are very popular nowadays, such as C and C++. We have languages that are memory safe and are also very popular, such as Java, Python, Go, C#. We have languages that kind of are trying to be successor languages to C, but that don't promise to be memory safe, like Nim or Zig. Those haven't caught on significantly in terms of traction yet, not in the same way that Rust, which fills all three of those, has. All right, so you might be thinking, well, that's great for like actual developers, but like Cindy, you reverse malware. Are malware developers actually using Rust? The answer is yes. So I went and collected some public reporting from 2023 and 2024 about Rust malware. And there's quite a few interesting entries in here. So I don't know if there's anybody here that worked that remembers the Ivanti Connect Secure vulnerabilities back in January and the mass exploitation of those vulnerabilities. So there was actually an interesting downloader that was dropped by somebody on compromised machines after they exploited this vulnerability. And publicly, it's called Krusty Loader, and Synactive has a great report on it. Another interesting entry here is the first one on this list back in 2023, where a North Korea Nexus group actually used Rust to write a piece of macOS malware. And that was actually like the last stage in, I think, like a 3 or 4 stage delivery chain. So you can read the headlines there as well. There's quite a few interesting entries. Of course, the public reporting is only the tip of the iceberg, right? This is where I have to do the vendor pitch. CrowdStrike Falcon Intelligence customers can read through our reports portal more threat intelligence reports about Rust, a lot of which I contributed to as well. So I just collected some numbers here, like roughly to illustrate what we're seeing on our end in terms of prevalence. And I didn't just like type in Rust and like, everything that mentions the word Rust. These are actual reports that significantly have to do with Rust malware. So we had 13 reports in 2022, and mostly at that time, it was just used by a few ransomware developers. So Alpha Spider and Hive Spider, which are names for the developers of Alpha, Black Hat ransomware, and Hive ransomware, respectively. In 2023, we saw a bunch of people start using Rust a lot more. There's 29 reports there. I think the emojis there just demonstrate my reaction to this, where I'm like, okay, I can't let everybody else, I can't let just the people who are working on those adversaries reverse this anymore. I maybe need to learn a little bit myself too. And so just so far in May 2024, we have 13 reports on Rust malware, and now we're seeing downloaders, loaders, backdoor, ransomware, inspo stealers, etc. So really a broad range. So yes, it's becoming a problem in terms of frequency, scope, and sophistication. Frequency, you can see previous slides. In terms of scope, we're seeing it both being used for malware in targeted attacks and also commodity malware that's just deployed opportunistically. So stuff you would see on like Google ads, like fake Zoom installer, right? Those are now being written in Rust, some of them. And in terms of sophistication, we kind of went from like, oh, cool, full-featured ransomware. They spent a long time developing this, to stuff that's just very simple, like the very simple downloader that we'll be building today. So I have a plea to everybody who is working in a position where they can name malware. It is time to stop naming Rust malware with names like Rust Downloader or Rust Loader or Rusty Stealer. Please, because I can't keep track anymore. We're at the point where something being written in Rust is not really distinguishing anymore. It's like naming a piece of malware C++ rat by now, right? It's not special. All right. So you might be thinking, well, Rust famously also has a steep learning curve. How much Rust do I need to know? We've all been this cat at some point. So we're not going to be able to learn all of Rust today in the limited time that we have. But I do strongly believe that it's important to understand some Rust source code in order to be able to reverse it. There's two reasons for this. The first is that Rust is a very different language from C. If you took a look at the code in that repository that I sent out, you'll see that it looks quite different from what you would write in C or even C++. We're going to need to take the source that's emitted by our decompiler, which is still nowadays pseudo-C, and try to think about things one abstraction layer up from that. Because it turns out that a Rust developer can write like 1 or 2 lines of code, and when we see the result of that in our decompiler, it can be something that's very large and recognizable. The second reason is that the Rust standard library is written in Rust, and the Rust compiler is also written in Rust. We have the benefit of both of those things being open source. And they're open source, we can go and look at them. And sometimes we will need to go and look at them if we're trying to figure out something that we're seeing on the reversing end. Okay, so we are here at the setup and tool slide again. I think 10 minutes has passed. Hopefully you're all set up by now. This is just a duplicate in case you need to like do it last minute. So from here, we'll be going into a slightly more hands-on part of our presentation. And I will have a drink of coffee. All right. So I'm now going to be sitting here because I'm going to be typing now. Um, but if everybody's comfortable and mostly set up, and it's totally fine if you're like, hey, I don't want to do this. I just want to like watch what you're doing in the workshop. That's totally fine as well. So we will be moving on to the next slide here. All right. So as part of that setup, I asked you to do a few things. One of them is to make sure that you can run the tool Rust up. So we can go over actually to our little VM here. And by the way, I realized I really should have put the password for the VM on the setup instructions page as well. The password is user as well. In case you're like, oh my God, I'm logged out and she didn't put the password. Why? Um, can everybody see this this terminal from the back? Is the text big enough here? Excellent. Okay, so yeah, just make sure that you can run Rust up. Once you do that, it should print help output like this by default. You can see that Rust up just tells you what it is. It says, I am the Rust toolchain installer, right? So if we go back to our slide over here, so Rust up allows you to do a few things. It lets you update installed toolchains. So if you want to update from Rust 1.770 to Rust 1.771, which is what we'll be using today, it also lets you manage cross-compilation support. Rust has pretty good support for cross-compiling across different operating system platforms. That's another reason why, for example, ransomware developers who target both like ESXi systems and Windows systems have been writing their stuff in Rust. And it's also possible, actually, to install multiple Rust toolchain versions side by side. This is most important if there is a language feature that you want to try out, and there are some that will be useful. So you can just grab the latest nightly build of Rust and have that feature. So if we go back to our VM here, and I don't like how this is cut off at the bottom. Let's see if we can change that at all. Okay, I'm just gonna, we're not using the full screen real estate, but that's okay. Just so we can actually see stuff on the bottom here. So one thing that we can do actually with Rust up is we can just show the tool chains that we have installed. So I'm going to do that right now. So with the preset up VM, you should be seeing something like this, where you both have the stable version of the toolchain and toolchain version 1.77.1. And those are toolchains that are just installed side by side. Okay, back to our slide. All right. And I do want to note something here, which is that we're now in a language ecosystem where developers can trivially grab the next stable version of Rust. If you've worked in like C and dealt with like different versions of vendor compilers and the long release cycles that those have, this might be a very different world to you. A new version of Rust comes out every 6 weeks. They have a very good release process. I don't think they've really ever been late with that. So this has some implications for us as reverse engineers, right? We're not dealing with a language, compiler, or standard library where changes occur on the order of years. We're dealing with changes on the order of weeks, right? And we can actually run Rust up update as well in our VM. I don't actually know what the latest stable version of Rust is, but I guess we'll find out. Yeah, it's we're now on 1.78. Came out on at the end of April. And that's one command. And stuff is downloading. There's a few components here. Rust C is actually, well, that disappeared. Rust C is actually the Rust compiler itself. And of course, there's a whole bunch of other stuff that comes along with it, such as the latest version of the standard library and some other tools. And that should be finished. That's it. We now have Rust 1.78.0. If we do Rust up show, wow. So it doesn't show the 1.78.0 as a separate toolchain because I just said, please grab the latest stable one. So this has now been updated from whatever my last stable version was when I made this VM to 1.78.0. But you can see it's pretty trivial for us to just grab the latest version and start using it. Back to the slide. Okay. The other tool that I asked you to make sure that you have installed is Cargo, or make sure that you can run is Cargo. Cargo is a tool that you'll actually be interacting with the most as a developer. It's the general all-in-one do things with my binary tool. It's the thing you use to build. It's a package manager. It's your test runner. You use it to initialize new projects. So if you're used to other languages where maybe there's a separate package management system, then this might be new to you as well. But I've got a screenshot here of crates.io, which is Rust's central package repository website. So a crate is Rust's terminology for a package or for a library. And that's why I've got like the little box emoji up here. But if we actually go there, right? You can see that there's a whole bunch of libraries that are just publicly available here. And if we go to like any of these pages, I don't know, let's do Serde, which is one of the most popular Rust libraries. The instructions right here are literally just use cargo, cargo add Serde, and that will add it as a dependency to your program. So simple as that. All right, and back to the slide. Oh my God, I have closed my entire presentation because I closed Chrome. Let's go back here. Pop. Okay. And we will find our way. One moment. Open up the speaker view again here. All right, cool. Okay, so now let's actually build our own Rust binary. This is kind of what we're all here for, is actually doing something with the tools that we have installed. So we're going to build a very simple downloader. As I mentioned, it's going to download and run a shell script. This is actually not that far off from real malware that we see in the wild. Like there's some downloaders we see that are basically about as simple as this. So I will pause here. Just for the people in this room, is anybody using Windows for this workshop? Okay, yes, we have one person. We have another person who's using. Okay, all right, cool. So just note for you, if you are using Windows, the sample code that is provided downloads and runs a shell script, which is intended for Linux and Mac OS. However, we can adapt the exercise quite easily to run on Windows as well. So when we get there, I'll provide some instructions on how to do that and what to use. Um, so let's get into it. Yes. So can everybody see these instructions from the back? Or should I zoom in? Okay, everybody is good? Okay, cool. As I mentioned, Cargo is like our main like developer facing tool that we're going to be interacting with. One of the many things that allows you to do is set up a new Rust program. We are going to go ahead and do that. I'll switch back to my VM here. One moment. All right. If you're in the VM, there is already a folder there that should be there for you called Rust Reversing Workshop 2024 with the source code of the finished downloader available. Just for the purposes of demoing stuff though, I'm going to make like a new folder and a new project, and we're going to walk through all of that. Let me just make a new folder here called Live. Okay. All right. So, as per the instructions on the slide, we're just going to run cargo new and the name of like our project or our binary that we're going to create. So I'm going to put down the microphone here, because otherwise I have to type with one hand. Okay, and if we now look at what's in our directory, we now have a new folder called Simple Downloader. If we go into it, you can see we have a couple of files here. If you're in this VM as well, there is a copy of Visual Studio Code installed with the Rust Analyzer extension pre-installed. So that should let you get set up with having like nice autocomplete and type hints and such for your Rust binary. So I'm going to open VS Code right now, and just so we can start taking a look at some of these files. If that decides to ever open. Oh my God. Maybe this was a mistake of running Zoom and like my VM at the same time. Zoom is very resource heavy for some reason. Oh my God, I don't have Kit. That's fine for now. Okay. And we'll close this. I was doing this before. Okay. So I'm going to zoom in a bit here as well. Can everybody see this from the back? Awesome. Okay. You'll see that if you look inside your source folder, there is a default main.rs that's just created for you. And it's your classic hello world. This print line exclamation mark here is just a macro that prints things. The other file that got created that's important here is this cargo.toml file. I'm going to hide the mini map here. And one second, I'm just going to turn on word wrap. Cool. Okay. So this is your like build configuration here, essentially. We've created a new binary package called Simple Downloader. This is the like your version of your package. There's something called Rust editions as well, which is kind of how Rust tries to deal with backwards compatibility in the faces of releasing every 6 weeks. But you'll notice here that, like, in contrast to, say, I don't know, a CMake file or like even a make file, right? This is like pretty minimal. Like, there's nothing here. Where's the configuration? What's happening? Um, so a lot of things here are just defaults, right? They're defaults that Cargo provides for you, and that unless you want to override them and change them to something else, you don't need to specify anything here. So this is one way where Rust makes the developer experience very easy. All right, so by default, it also creates it as a Git repository. So there's also this git ignore here, and I've got Rust Analyzer running, so create a target directory, but that's fine. We'll get into that. And again, if you are using VS Code, I do really recommend the Rust Analyzer extension. It is the official Rust programming language extension, and you get type hints, you get autocomplete, you get help. It will do the nice things for you. If you're using a different editor, then I think there are equivalents of Rust Analyzer or versions of Rust Analyzer for those as well. Something language server protocol. I don't know. I just use VS Code. Okay, so we'll toggle back to this briefly, and then we'll go back to our slide here. Awesome. Okay. So this is some of what I just went over. Here is the default main.rs. I think it's created for you. The default cargo.toml file. And as well here, I'll just show you if you are like, well, I want to know what the defaults are. Like, I don't want to just you to tell me there are defaults and, not know what's going on. So I have a link in the slide here to the Cargo book, which is the online official documentation for Cargo itself. There is a section in that book called Profiles, which actually just tells you about the definitions of all the settings that you can have, and the default settings for each build profile. So it's all documented here, and you can look at it if you're like, well, I want to know what's actually going on in my build. Okay, so now let's actually like build this. We've gone long enough, like 34 minutes without doing anything. All right. So again, Cargo is your main developer-facing tool. So we're just going to use Cargo build. Right? There's a default build file that's already set up for us. So if we go to our VM here, and if we go back to our terminal. And I'm just going to clear this so that we're at the top of the screen. So you do want to make sure that before you do a Cargo build, that you're in this root of your in the root directory here of your project. Because Cargo does expect when it's building to find a cargo.toml file. Again, that's your build configuration file in the same directory. But once you've got that, and if you're in the right place, we'll do Cargo build here, and that's done. So with the default profile, which is the dev profile, this is an unoptimized build, right? With full debugging information. It's going to be gigantic, and it's going to have all the symbols. So if we go back to our slide here, okay. And again, if you do want to know more about that default dev profile, that's in the Cargo book, which I have just showed you, and that dev profile is right here, and you can see there's no stripping, debug is true, optimization level is 0, and so on. Okay, now let's run Hello World. All right, 36 minutes in, let's run Hello World. So Cargo, it can do everything. It can also run the program that we just built, simply with Cargo run. All right, so If we do that here, wow, amazing. We have hello world. Um, yes, please clap. Don't clap. Thank you, thank you, thank you, thank you, thank you. Yeah, that's what we're all here for, right? Um, yeah, so notice that it does tell you, like if you're like, well, I don't want it to just run things for me, I want to know where the program actually is. It does tell you where the build file actually is. So we can go and look there. It's under a folder called target, and then a folder called debug, because this is our debug build. And then this is our actual binary. So I'm just going to run the file command on there so that we can see what type of file it is. Uh, simple downloader. Cool, 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 cool. All right, we have an L file. It's for Linux. It is NOS-driven. It has debug info. If you look inside it, there are full symbols. All right. And I think we can look at how big this is as well, because it's going to be quite large. One moment. Okay. So you know, that's quite a that's quite a large file. This isn't bytes, so again, this is a unoptimized build. That's kind of what we expect. All right, and if you do open up that file in your favorite disassembler or decompiler tool, this is a screenshot of Binary Ninja that I took. You can see that you will be able to see that there are symbols like everywhere in that binary. If you look at it with just something like whoops. If you look at it with just something like readelf, which we can do here. One moment. I'm gonna, because I don't know how to use readelf, I'm gonna do readelf-a, which gives me all the information. Target debug, simple downloader. Yeah, and we can go up here and look for the symtab. So it's a little bit hard to see here. I'll expand this. But these are the symbols that are inside your binary. Now they are mangled. They're the Rust like mangling scheme, unlike the one for Nim, is actually pretty well defined. And nowadays, with the latest versions of IDA, with the latest version of Binary Ninja, with the latest version of Ghidra, they should be able to demangle all of these. If they're not, you may need to upgrade what you have, but they should show up like not like this if you actually look at it in a disassembler. Okay, so let's go back in our slide. Let's go over here. Oh yeah, I went a little bit too far. Okay, cool. So you're like, well, that's huge. This is Hello World. Like, I actually do want a release build now. Well, you don't need to set it up. Cargo can do it for you. Right? All you need to do is cargo build -- release. That'll give it, and that will invoke cargo with default release profile rather than default dev profile. So we can go and do that right now. Uh, let's go over here. Let's go over here. We'll clear this again. And we'll do a cargo build -- release. Okay, that's built. It's pretty simple. It's hello world. We can also do cargo run -- release to run rather than the debug version of our binary, the release version of our binary. Amazing. You'll notice that it also does tell you here that it's running target / release / simple downloader. It's in a different folder. So we can go and file that again and just take a look at it. All right. So we have another elf file, but notice this is not stripped, right? Um, if you're used to like release profiles and like other programming language ecosystems, you might assume that release binaries are stripped of symbols. But we can actually go and do our readelf-a here, target release simple downloader, right? And wow, look, everything is still here. Um, so if we go back here to our slides, this still gets a lot of malware developers. Like we get binaries that show up on our desks, right? And it's like they're like optimized, and if you actually look inside at the code, it's pretty clear that they're optimized. But all the symbols are still there, so they like still look like this, and you have everything there, and you can like still muddle through it, right? Um, so I think developers and especially malware developers are starting to realize this, that like their release builds are not stripped. But like for all 2023, like the binaries that we were seeing were like full symbols, like it's Rust, nobody will be able to reverse it. Well, they didn't realize this. So we can't rely on this, of course, because it's actually trivial to remove the symbols if we want to, and we will do that in the next step. Um, but again, this is documented, but of course, nobody ever reads documentation. But if you go and look again in the cargo book at the release profile, and you look at exactly what options it actually uses, strip is still none here, the same as it is in the dev profile. All right, so we are an enterprising malware developer. How do we actually remove symbols? Um, So this just with the option we just looked at, we want to set strip to true. You can also set, oops, I got to highlight it here. You can set strip to true. You can also set it to strip equals symbols. So this is, again, an example of you don't need to really write anything in this cargo.toml file unless you want to override a default option, which is what we're going to do now. We do need to make a new section here called profile.release, just to indicate that we're overriding something that is normally a part of the release profile. So we'll go over to our VM here, and we will go and do that. And I'll just toggle open VS Code here. We'll open up our cargo.toml file. We'll make a new section here. If you're not familiar, by the way, with TOML files, it's just a like configuration file format. You might be like, what is TOML? I've never heard of this before. You can kind of think of it as a really fancy INI file if you're familiar with those. Similar syntax, but not exactly the same. So let's go and set up our stripping here. And we'll save that. All right. So now that we've got that in our release profile configuration, we can go ahead and just do cargo build -- release. Now I'm actually just going to do cargo run -- release. So cargo run is smart enough to realize that, oh my God, you have changed something. Oh my God, I need to build the binary again before I run it. So we can just do that. Cargo run -- release, build and run all in one step. Boom, there it is. Hello world. And it tells us again, right? We ran target release simple downloader. We can go and file target release simple downloader. Amazing. It's now stripped with just one trivial step. So malware developers, you should really know this by now. I have shown you exactly how to do it. So if we do readelf-a again on that file, again, I like don't really know how to use readelf, but like this is the DINSIM table. This is some stuff that will just be there in dynamically linked Linux binaries, but our nice symbols that we previously had with all of the Rust specific symbols are now gone, right? So this doesn't have a symbol table section. It's gone. It's stripped. Cool. I need to get out of my VM to Alt Tab. Okay, this is what we just did. So I'll skip this. This is a screenshot of Binary Ninja without symbols. It's also what we just did. All right, so we're not here to just build Hello World, right? We want some download functionality. So again, there's a very rich and mature like open source library ecosystem with some like popular libraries that you can just pull in for adding things like HTTP client functionality. Um, so this is a library called Request. It's like the word request, but cute, I guess. Um, so we can go and actually search its page on crates.io, which is again the Rust central package repository. I'll just reuse my browser tab here. Mm-hmm. And you can see there's a nice README here with like links to documentation and examples and so on and so forth. The installation is just one step, cargo add request. Now don't run that yet because we do need to pass an extra flag to this. If you've already run it, that's fine. That's okay. Like you could just do the next step again and it should do the correct thing. But again, right, cargo is our main package manager. It's you just, if you want to add a dependency, that's all you do. So we are going to go back to our slide here. Not the zoom controls. We want our window here. Okay. I think I need to zoom in maybe a little bit here if okay, that's it's not cooperating. So we're going to do this, which is cargo add request, but with the blocking feature. The reason for this is that today we're going to be writing asynchronous downloader. It is not going to be asynchronous. And the reason for that is because teaching synchronous Rust code is hard enough. I really don't want to teach async Rust. The code looks somewhat different. So we're going to keep it simple today and just use request as in its synchronous form. So I'll clear this and do cargo ask request dash features blocking, and hopefully it'll be bigger there so you can actually see it. All right, and we are done. Oh my God, I have done the incorrect thing and added a space between the dash dash and the features flag. So now we have added the blocking crate as well as the request crate. Terrible. So let's do that again. We're gonna add request with the blocking feature actually for real this time. Um, Now, if we look in cargo.toml, we now have, well, I have, because I typed this wrong, a dependency called blocking and a dependency called features. So we can just go ahead and delete those from this file because we actually only need request. So you can see here that this is declarative, right? You just say what library you want and what version of the library that you want. Now, most Rust libraries are open source, and so our machines will be building requests from source in a moment here once we actually built this. But all the adding the cargo add did was it added this line to our cargo.toml, and it also downloaded some additional files, such as the source code. Well, it also downloaded some additional files, such as the help, so that we can actually use request in our source code, and then we can build it. So we haven't built our library yet. So let's go back to our slide here. One moment. think I went back a little bit too far here. All right, cool. Okay, so that's our updated cargo.toml right there, which I have just showed. All right, now let's actually write some code. Um, I am, so this is like, I don't know, 10, 11 lines of code. We're just going to start with making a request to this URL right here. This is the URL of the shell script that we're going to download. You might notice that this is the exact same shell script that you downloaded to install Rust in the first place. This is why it's very benign. Like, you have already downloaded this. You have already run this. It will be fine. So again, most of the actual heavy lifting here is done by the request library, right? This is 10 lines of code. The code we need to write here is pretty simple. This does look a bit different than C though. So let's go through this together step by step with just the help of Rust Analyzer as well in VS Code. So I think there are some people copying this down too. If you do want to do that, I'll give you like another few moments here while I have a drink, but we'll also be kind of going through this together. So don't worry if you don't have all of it copied down right now. But I will have a bite of my bagel and some of my coffee. Okay, I think some people are heading out, so this might also be a good time to just take like a 10-minute break. We're here for 3 hours. We can take a break. You can go to the bathroom. I'll leave the slide up. You can copy down the example, and we'll come back. I think it's 9:54 a.m. right now. We'll come back at 10:05. If I can, yeah, okay, 10:05. So we'll resume at 10:05 here. I'll leave the slide up. I don't know if there are any questions so far in either here or in the live stream chat. Stunned silence. That's all good. It's all good. If you think of anything, we'll be taking kind of pauses during the presentation. So if you do think of anything, you can always ask it at the next pause as well. Yeah, so the question was, can you explain the bangs or the exclamation marks that we see in the print line lines and also the panic lines? So print line and panic there are technically like they look like kind of function calls, right? Where you have like print line bang and then like brackets, arguments, and brackets. But those are actually technically not functions. They're macros. They Rust has a pretty mature macro system as well, which is not at all like C's macro system, where you're basically doing string matching. You can work essentially on the abstract syntax tree of like you can go through the parse tree of the program essentially and grab out like arguments that are passed with the macro. So printline and panic are Panic is kind of similar to printline in that both are doing string formatting. So the syntax that I've got there just does it inline like you would see in like Python with like f strings, but you can also have has like multiple arguments to each of those with like the things that you want to print. So it's a bit easier, right? Well, I think really you can only it's a bit easier to implement that as a macro rather than like a real function. Rust because of the macro facilities that Rust provides. And so the bang there just indicates that this is a macro and not an actual function. But that's a very good question. Thank you. But yeah, I have a lot more material, so like look at that.
But this is like going as fast or slow as water.
Yeah, kind of. I did an internal version. Yeah, and but with that I only really had so I felt like so this is
So we're pretty relaxed in terms of
yeah. I mean, we'll see. Like, we'll get to later parts. But try to pace it so that people can.
Perfect.
Look. Yes. I should be able to provide. Hey, like you're filling in. Yeah. Did you check your phone? Oh, nice, 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 nice. Thank you, thank you. You're welcome. I could not. Yeah. Thank you so much. Yeah, I try. Yeah. And I walk through like. Yeah, yeah, yeah. Like, how long? Yeah. Well, I did two other this up. Oh, yeah, yeah. It's like every things. Yeah, that's good to run by it. Obviously, yeah, I like that. That's not even all. It's not all rest up. Like, we talked about. Probably not. Like, I mean, I know it's 30 days. Like, yeah, yeah. Yeah, the rust is still yeah. It's definitely. Yeah, I think sometimes like it's like fuzzy and people are like, oh, well, I don't want to analyze this water, even the city. Yeah. You become the rest person. Yeah, yeah, yeah. Kind of, yeah. But yeah, it's definitely. Yeah. I'm trying my best. I was also asked to make the larger. So yeah. Oh, did someone like message you just now while watching the live stream? No, no. Oh, okay. It's just that. I had to give myself. Oh, okay. Yeah. Yeah. It's kind of like you should be sassy when you make it like something. Yeah, yeah. I mean, like, it's cool because it definitely shows you some background. Yeah. Like, I don't. I haven't avoiding development. But like, I feel like having an external perspective, like inside out, kind of helps. But now, especially that I think I was mentioning yesterday how now I'm like paying to learn how to use Git, and I'm like that. Yeah, now I can really do it. But this is so cool. Like, I love how. Because Jackie, who I mentioned yesterday, she's like. Actually, I just oh yeah, you should. I'm just like, yeah, no, it's good. I will. Hello, everybody. It is 10:05. We will get started again here. I think there's a few more people making it in. But let's all continue. All right. So, as I mentioned, when I introduced this slide, this is really literally copying the example from the request documentation, right? This is not that complicated. I went here, I looked at this. This is the blocking version of request, as I mentioned. And I was like, cool, yeah, I'll copy this. I did make a few changes just so we have like nicer error handling with air quotes. But this is about as simple as it gets. So we will. I don't know if I can. I don't remember if I opened this in a new window or a new tab. I don't want to close my entire presentation. Okay, YOLO. Okay, cool. All right. So I'm gonna go through this kind of step by step here in VS Code. We're gonna have like type hints and everything, and I'll introduce some of the things that are in this code as we kind of go along. So let's go back to our VM here. Again, the password is user. I really should have put that on the GitHub repo. Go back to our main.rs here. Okay, cool. So I'm gonna try to like type with one hand and use extensive use of tab complete because I'm also holding the microphone. All right, so we're gonna delete our hello world here. Goodbye, goodbye world. All right, so starting with the basics, we have a let here. Let is the keyword in Rust to declare a variable. If you're familiar with JavaScript, or I think there's other languages that do this too, that's the same keyword. We're gonna name our new variable here request result, because it's gonna be the result of our request blocking get. Okay, cool. So you can see there is a big type hint here, and I'll turn on word wrap as well in just a second. Well, there's a big tooltip here that tells you, hey, this is what request does. Here's an example, blah, blah, blah. This right here, though, is the function type definition of request blocking get. So some syntax here. Fn is indicates that something is a function. This is the name of that function. In Rust, types are placed after a colon, after the variable name. So this is a URL of type T. So you can actually pass a variety of types into request blocking get. It's pretty agnostic about how you provide your URL, but in this case, we're just going to provide a string. And the return type is listed after the FN and the name and the arguments. There's a little like arrow. This is a dash and a greater than here. And then afterwards is where you put the return type. So the return type of this function is something called a result. This is actually a Rust equivalent of a union. So this is, you can think of this as a union of either a response or an error. This is one of the ways in which Rust does error handling, is that you'll see this pattern a lot where you have some function that can fail, right? And but that in the success case is going to give you back some data. But the type that you get back is not just the data itself. It can either be, it's a union that can either be the data itself or some sort of error. So that's what this means. We have a union, which is, we have a union type called result, which can either be a response or an error. Okay, so with all that said, I will now put a semicolon on here, so that's the end of this line. So we'll save that, and I'm going to turn on word wrap here. One moment. Okay. So Rust Analyzer is angry at me because, well, I haven't specified any URL here. So I am now going to specify a URL. And again, it's just going to be https sh.rust.rs slash whatever the actual thing is. Yes, I've got it here in my slide. Okay, so I'll type it here. And we can just provide this as a string literal. Okay, and a note here, if you are on Windows, again, this is the Unix, so Linux slash Mac OS version of the script that we'll be downloading. If you're on Windows, you can instead download the Windows version of the RustUp installer. So if you actually go to rustup.rs, which I'll go do that right now. And yeah, so you can see I'm on Windows right now, so it's giving me the Windows instructions. But you can also use the URL of rustupinit.exe. So if you go and grab, if you can go and download that instead, and run that instead with this downloader. Or if you have like some other executable like somewhere on the internet that you really want to download and run, you can also do that too. I will not judge you, as long as you have accepted the consequences of whatever running that executable will do. But I recommend this if you are on Windows and following along with this. Okay. So let's move on here. So now Rust Analyzer is angering me for a different reason. It's saying, well, this is unused and it's warning me that it's unused. Okay, that's fine. We will use it in just a moment here. Another thing that you'll see as well if you're using Rust Analyzer is that by default, it gives you like this little ghost type hint or this little ghost type that it annotates here. So one thing with Rust is that when you're writing it, even though Rust is a statically typed language, it does care about types. You can't just like pretend that types are whatever you want. You can omit types in a lot of cases when you're actually writing the code if it's obvious what the type is. So in this case, it's obvious what the type is. Rust Analyzer can even infer it. The compiler can also infer it just from the definition of request blocking get. But that's what this is. And I don't know if it's more confusing to leave this on or leave it off. But in the actual source, this bit right here is not present. Okay, so we'll move on here. All right. So now that we have a result union, let's do something with that result, right? Eventually, we do want to get whatever it is that was returned from this GET request, like the data from this GET request back, and we want to do something with it, right? So once this runs, this will actually make HTTP GET request. So after this line is when we do all the stuff with that request, with the result. So we're going to introduce another keyword here, which is match. So I will just type out some of the code here, and then I'll explain it. Okay, so match is you can kind of think of it as, I like making analogies for C programmers. The people who actually program in higher level languages might be like, you guys are living in like the Stone Age. But you can think of it as a switch statement. In some sense, this is a oversimplification, but you can think of it as a switch statement that's going to match on the type of whatever is in this request result union. So again, this is a union between a response and an error. Unlike in C, this union does actually have a like type information that's inside it. If you're familiar with C++, I think they're called variants in C++ 17 and beyond, then this might be familiar with you. Or if you're familiar with the term tagged union, this might also be familiar with you, to you. But long story short, we can open up this request result and we can inspect, okay, what is inside? Is it a response or is it an error? And Rust Analyzer will like be like, well, you know, like you don't have anything in here. We're missing two match arms, which are basically our two cases in this switch statement. So let's go and actually write those. So uh, the way that we're going to do this is we'll do one match on OK. So this is actually what the response field in this union is called. Um, and we'll put an underscore here for now, just so Rust Analyzer doesn't complain. And the syntax right here, the equals greater than, is saying, okay, if you do match, if the thing inside the result union is okay, which means it's a response, then do this. So we'll do nothing for now. And then we can do our other match arm here, which is the other field of that union. And we'll also do nothing here. And we'll save this. And if we hover over this, you can actually see that this is something this is the actual like type of our union. And this document says as well that the OK part of that contains the success value. So very technically, if you're like, I'm a Rust programmer, they're not called unions, they're called enums. I'm deliberately avoiding using the word enum here because enum has a very different meaning in both programming languages, and that's why I'm calling it a union or a tagged union. But yes, this is actually technically an enum. And enums and Rust are magical and beautiful, and I wish all languages had them. But for the C programmers here, you can kind of think of it as a tagged union. All right, so what we're going to do is in the OK case, we now have a bit of data that's actually inside this tagged union. So there's the tagged union has like nested fields inside it. So each response contains some data, and each error also contains some data, and we can do things with that. But in this case, we just want to grab the response itself and the error itself. So we're going to do that with just like this. We're going to have we're going to grab the response out of there. In the OK case, it's going to be of the type response, just as we have here. And we're going to grab the error out of here in the error case. And it's going to be of the type error, just like this. And again, this is just Rust Analyzer inferring what the type is. This isn't actually present in our code. So we'll save that. Now, that's not complaining because I misspelled it, but I did misspell it. So we'll do that. It's complaining because those are still unused variables. All right. And in the OK case, we can simply do a print line. So just like we did with Hello World. And we'll just print the response data that we received. Now, this isn't going to be like the actual like response, the actual like response data. It's going to be like some metadata, and then like there's a response data object that you can like look at if you want. But it's still useful. We'll see kind of like the headers of the response and so on. So we'll just print it out. So let's do print line here, and I'm going to use a bit of syntax here inside the print line that I'll explain after I type it. All right, so this is saying, please print and you can see Rust Analyzer. It's like, oh, I know what this is. This is the same thing. Please print the response variable in its debug representation. So again, if you're familiar with Python F strings, this might look quite familiar to you. And we also will do something in the error case. So we're going to introduce a keyword here or a macro here called panic. And the syntax and we're going to provide a panic message, which is just going to be a string that we can format in some way, in the same way that we can format the string inside the print line. So I'm going to type that here. Okay, great. So all this program is going to do is it's going to try to make a request to that URL. If the request succeeds and we receive a response, then print that response object. And if the request fails and we fail, then do something called a panic, which we will get to, and also print this what the error was along with the panic. Cool. So I think that's basically what I had on my slide. Yep. So we can go and build and run this now. So let's go back to our terminal here. And I'm just going to go ahead and build this in release mode. So again, it's just cargo build dash dash release. Now, if you're doing this for the first time after you've added the request dependency, it is going to take a while now because it's actually compiling the request library. So again, the cargo add step just downloaded the requirements to compile the library and added it to our cargo.toml build configuration file. But now that we're actually building our binary, we're actually also building the library, which is going to be statically linked into our binary. So it takes a bit of time, but we're almost there. And you can see as well that there's quite a few other libraries that are here, which are like not request. So this is request and all the dependencies that you need for request. So it's entire dependency tree. All right, we're finished that. Now let's just run our binary. This is a step where it is helpful to do this on a computer that has an internet connection, because otherwise then you can't actually download this. So my VM is connected to the internet here. So I'm going to do cargo run dash dash release to run the release version of our binary, which we just built. Cool. So if you've done that, you should be seeing some actual header information that you got back as part of the response, as well as a nice status 200, hopefully, maybe. If you're doing this on a computer without an internet connection, then you may see an error message and something that mentions a panic. So great, you have handled the error case, the case in which that request was not successful. And yeah, like we're pretty sure that this is like an actual request that was made. There's a nice date here, which seems legit. These headers seem like they're from, some S3 server somewhere, right? All right. So we have a binary now. So, we're an hour and a half in. Let's actually do some reversing, guys. We're going to run strings. It's going to be great. Okay. So again, our binary is going to be at where cargo run said it was, at target release simple downloader. So we'll go and find that. And of course, because we edited our build configuration already, this is going to be stripped, so we don't have symbols. So a realistic downloader case. All right. So what happens if we just run strings on this? Let's just go and do that right now. So we'll dump strings from target release simple downloader. Wow, there are a bunch of strings. Wow, I don't know what any of these mean. Wow, is there maybe a URL in here? Because I will grab the IOC and then, write the report and like go home, right? So if you've ever like dumped strings from a Rust binary, some of this might look familiar, right? There's some stuff that looks like, oh, maybe it's useful, right? Like there's some things that look like paths here. There's some things that look like error messages here. There's some strings that don't make a lot of sense. There's some things that are just part of like the ELF file metadata. And there's generally a lot of junk here, right? So let's start breaking some of these down. I will go back to my slide. If I can find my mouse. And this is my reference slide because I can't write all of this code just from my head. So this was my speaker view. But yeah, these are all the dependencies. Now, if you do want to view, if you're like, supply chain attack, right? There's so many dependencies of requests. What are all of them? You can view the dependencies on crates.io under the page for request. These are just going to be the direct dependencies. They're not going to be the transitive dependencies, so the dependencies of these. But you can at least get an idea of what the direct dependencies are. This tab is also useful, the dependence tab. So it's what things depend on request. So this is running the binary, la -da 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 -da. We already did that. So the headers, yep. Now we're reversing. All right, so this is our initial string triage. Okay, so let's actually look at these strings. So one thing you might know, if you've looked at Rust, or if you looked at Go, or if you looked at Nim, or if you looked at other modern cool programming languages, is that they all think null termination is no longer a good idea for strings, right? And same thing with Rust. Rust strings are generally not null terminated, and the strings utility, right? Strings1 on Unix systems tries to find strings that by looking for the null terminator. So this is, I don't think this address is completely correct anymore because this is from a different version of the binary, but the example still holds, where all of this is from a single null terminated string, right? So back in our strings view, right, all of this is what strings would show you. It would be like, oh, well, this is one string, right? But no, it's not. I went and just kind of manually separated these based on what made sense. But a single null terminated string that strings finds for you is actually all of these somewhat unrelated strings that just happen to be placed next to each other in the binary. All right. So let's say we're lazy reversers, right? We don't have time. And we want to go just one very tiny step beyond strings. Well, it looks like there is a lot of metadata in there, right? Like there's paths, there's error messages, there's things that look like they could be potentially useful. So just as a first step, immediately, we can get some very useful metadata from some of the strings that we dumped. I know this is extremely tiny, but we can actually get the version of Rust that this binary was compiled with, right? If you look at some of these paths here that start with Rust C, there is a big thing that looks like a hash here, and that's actually a git commit hash. It's a git commit hash of the main Rust language Git repository. So in this example, which is extremely tiny, we have Rust slash Rust C slash 7C F61E, and I won't read the rest of the hash. But we can actually go to github.com rustlang rust to that commit, right? And in this case as well, this says, okay, it's Rust C, blah, 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 the commit hash, and a path called library alloc source sync.rs. I think it's a bit bigger here, library alloc source sync.rs. That is a real path that exists in the main Rust language Git repository. It's part of the standard library of Rust, and we can go there. I should actually really set my computer to light mode, even though I love dark mode, it doesn't work that well on the projector. But I will zoom in just to show hey, we're on this commit. It's a real commit. It exists. It's not on well, they use tags and then some branches, but this is a real commit that still exists. It's part of the Rust 1.771 release, and this is a real file that exists as well in the Rust standard library. Okay, so if you've kept track of all of the words that I just said, all of the terminology that I threw at you about the tools, you might be thinking, okay, well, you just said this is part of the standard library, right? Library Alex source sig.rs. But the beginning part of the string, right? This is Rust C, which is the Rust compiler. But the compiler is not the standard library, right? Those are different things. So why are these both here? So far in this presentation, I've kind of just been saying Rust 1.77.1, not the Rust compiler 1.771 or the Rust standard library 1.771. So now I will clarify that a little bit. So the Rust compiler, the Rust standard library, they're in the same repository and they're released in lockstep together. So this is, again, unlike maybe some other programming languages where you have like different compilers and a standard library, but that has different versions, and some people don't like using the standard library, and so on. With Rust, everything is quite centralized. And like when you talk about the language, you're talking about basically one implementation of the compiler and one implementation of the standard library. Now I know there's like exploration of other compiler implementations for Rust, but really the only production ready one is like the main Rust C compiler. So when we talk about Rust 1.771, we mean both Rust C 1.771 and the Rust standard library version 1.771. This is kind of the most obvious if you look at any of the release notes for any of the versions of Rust. So I've got a screenshot here of like a site that just aggregates release notes for Rust. Oh my God, 404. Oh my God. And now I've lost my slides. This is terrible. A moment. Okay, this is a screenshot from when this did not 404. I think I just did the URL wrong. But in the screenshot here, which just has a summary of the release notes for 1.760, you can see there's a section for the language, for the compiler, and also for libraries. So the section for language is things that changed in the core language itself, right? This would be things like, oh my God, we have added a new keyword. I don't think usually the changes are that drastic, but that would be an example of a change that would go in that section. The compiler, like there's some things that happened in the backend of the compiler. There's a new optimization that we added. There is a new architecture that we're now supporting for cross-compilation, etc. And libraries, right? In the standard library, we've changed the implementation of, I don't know, std string, or we've added some new thing to the standard library. But all of these are under the same bundle of changes in Rust, the language 1.76.0. So that's why Rust C and the Rust standard library, they're all in the same repo, and that explains this as well. All right, what else can we get from these strings, right? Well, we can get quite a useful piece of metadata, which is the cargo home path of the machine where the binary was built. So those strings were from a previous version of the binary that I actually built on my real machine and not a machine with username user. So you have home/cxiao. And this can actually be quite useful if you're into threat intelligence by CrowdStrike Falcon Threat Intelligence. If you're into threat intelligence, this can be useful for tracking adversaries, right? There are some adversaries that just have a few build machines that they reuse, and it's quite obvious who they are. And you kind of see the same names come up, and they kind of, you recognize them. They're doing stuff, and that can be a useful piece of metadata for clustering samples. So if I write a piece of malware, I build it on a machine, you kind of know, well, it's somebody named C Xiao who built this malware, right? You can also see some, but not all, of the dependency tree for the binary. So this is actually the full path, where the full string where that path comes from. And you can see like something registry, something source, something index creates.io, which is where I got this particular dependency from. And the name of library, in this case, Tokyo, one of the most popular Rust async libraries, and a version 1.37.0. And if you look inside the strings of your binary, you'll see like a whole bunch of paths that are like this. But this is not the entire dependency tree, right? If we go and look in our VM again, password is user. We go and actually look in here. There's some stuff here, HTTP 1.10, bytes 1.60. But if you actually do like extract all of the paths and count up like all of the library paths that are here, it's actually much less than that giant dependency tree that we had while we were actually building this binary for the first time. And I think it is gone from the scroll back of my terminal because there's so many strings in here. But it's not the entire tree. So why is that? Why don't we have like some library names in here and some of what look like source file paths? Why don't we have the entire thing? And yes, there are tools out there as well to go and extract that metadata from like these source file paths. There's a really great tool called rustbin.info, written by somebody called NoFix. Shout out to NoFix if you're out there watching this presentation. You're great. Which you can go and check out on GitHub. And it's just written in Python. It's fairly easy to use. And it will actually tell you, based on that information, that metadata that we have, first off, what the commit hash is for rustc, what the corresponding rustc version is, and also what the dependencies are and their versions. I don't recall if I actually put rustbin.info in this VM. I guess we will find out. I did not put it in this VM, but that's okay. You can go and check out rustbin.info, and I've got an example of its output here for the binary that we just built. So this has quite a lot of dependencies. You can see that there's quite a few here, but again, even though this list is long, it's not the entire list that we saw a few slides back over here. This is actually much longer. Okay, so we're going to take another step beyond strings. We know that we can get metadata, right, from this stuff. We know that it's useful for potentially identifying the developer. We know that, hey, there's some information about libraries that were used in here. But why, right? Where did these strings actually come from? Why are they here? So now I will introduce the concept of panic. So different programming languages have different ways of handling errors, right? And there's different classes of errors. There's some errors that you can deal with in your program and you can kind of continue on. But there's other errors where if this happens, there's really no point for your program to keep going. It's unrecoverable and it's usually unexpected, right? You can't catch it, you can't handle it, you might as well just give up. In our case, we deliberately introduced a panic into our program. We did that previously with the panic macro. So if you recall, that's this bit right here, where we say, hey, if we're not able to make a request and get something back, then please just panic and print this message. So in our case, right, we're writing a downloader. If there's no thing that's downloaded, then you might as well exit at that point. Now, the standard behavior of a panic is that the current thread will just exit after cleaning up and unwinding and calling destructors along the way. So it is a clean exit by default. It can be added deliberately by the programmer, like we just did in our program. But there's also lots of places in the standard library and in third-party libraries where it can occur, because there are lots of places in the standard library and in third-party libraries where something unexpected can happen. Um, a big one in Rust by default is if there is a bounds check failure at runtime. So by default, your program is going to check at there's going to be code in your program at runtime which checks whether you're indexing something outside the bounds of an array, right? And if you are trying to do that, then the program will stop. It will crash. That is a way to prevent some classes of memory safety issues. You can turn it off if you don't like the performance effect, but by default, that's something that does happen, and it's all over the place. Another thing is assertion failures, right? You can say like, hey, this thing should just never happen. If it does, please immediately exit. I think it's pretty typical for other languages as well. And related to that is if you have some malformed or some like unexpected state, right? Where you're like, we should never have been able to reach this state. If we're in this state, something is very wrong with our program. So this is like kind of abstract, but actually, there's some good like concrete examples of these conditions in some of the strings that we just looked at. So if we go back to a couple of slides here, to my like nicely split string slide. There's some examples here that are interesting. So this error message cannot access a thread local storage value during or after destruction. This is saying, hey, there's something in the TLS storage of this binary, but something else was destroyed, and the value that should have been here is no longer here. I am going to exit now. So this is actually an example of a condition in which a panic can occur, and when a panic occurs, this error message will be printed out. Another thing is cannot start a runtime from within the runtime. This happens because a function attempted to block the current thread while the thread is asynchronous, right? So please don't do that. We're doing things asynchronously. That's a bad idea. Another thing here is an arc counter overflow. So this is referring to a type of reference counter that can be used in Rust. If your counter overflows, if your like reference counting counter overflows, they can no longer count objects, and that's very bad. And that does compromise like your entire program, and things are probably not going to work. So please just immediately exit. All right, so that's where those messages come from. But I mentioned that like there's some paths and there's like a dependency tree. So why are those there as well, right? It makes sense that the error message that is associated with the panic would be there, but what are those other paths? So so we introduced a manual like panic into our binary in the case where we can't make a request. Let's go and actually introduce that like ourselves. We're gonna use a different URL here. So not like the real rust up .rs shell script URL. We're gonna change that URL to like localhost 1234. And I don't have a server or anything running inside my VM. Nothing's gonna be able to make a connection there, right? So that's actually going to trigger our panic case. So we can go here and we can just edit our program here. So I'll change that URL. Okay, we'll save that, and we can simply cargo run -- release. So again, cargo run -- release is smart enough to both build and run our binary if something has changed. Oh my God. Wow, how unexpected. Thread main panicked at a file path here. Source main.rs. Oh, a line number here. Oh, this is actually a column number here. And here is the actual error message that we have. Error making request. So you'll recall that in our source code here, we actually did type this out, error making request, and then the rest of it is the error that's inside this the error field of the result union, which request blocking get provides to us. So the rest of that error message is from request blocking get, and it's very helpful. It's very nice. Error sending request for URL, blah, blah, blah. And we can even get a backtrace if we want with this environment variable. But you'll notice here that this actually gives you a lot of information, right? This is trying to be helpful and say like, wow, you are a legitimate programmer debugging why your web server or something doesn't work. Oh, maybe you want to see the line number and the source file where it didn't work. Okay, well, this is very useful. We can go and see like, oh, let's go to source.main.rs and let's go to here. And wow, it was indeed this line 8. And we can actually go to line 8, column 13, and that's like the beginning of this, right? So it's very nice, it's very helpful. However, right, uh, if you're a malware developer and you're writing like some downloader client, you don't actually need this, right? But that information is still there. So, let's see, it's 10:47. I don't know if we have time to go into this in a lot of detail. Let's see what my next slide is. Looking at guts of panic, the metadata struct. Okay. All right. So, uh, panic in our unstripped binary. Yeah. All right. So let's look at this. 1 hour and 48 minutes in, we are going to open Ghidra. Amazing. All right, everyone. So, in our VM, you can either, so this is a step where you can use a disassembler or decompiler of your choice. Nothing we're going to do here is like specific to Ghidra in any way. The decompilation may look a bit different, but the concepts are the same. I'll use Ghidra here just because it's free and accessible to everyone. But if you look inside your VM, if you're using the pre-configured version of the VM, on the desktop, there is a shortcut that just says launch Ghidra, and you can double click it, and Ghidra will hopefully open in a second here. Oh my God. Okay. I'm glad that worked. And there is a Ghidra project as well that is already present, and I think should be open in the VM snapshot already. It's and it should just be called Rust Reversing Workshop 2024. There should be 2 binaries in there. One is a stripped version and one is an unstripped version that is included for like easier illustration purposes. Now this is kind of small. I am going to open a like one of these. I'll open the unstripped one first, just to see how the listing and everything looks. I might need to make some adjustments here. Hello, Ghidra. Are you okay? Are you present? Uh, this is okay. All right. So I might not be able to do anything about the UI, about like the UI elements here without restarting the program, but I can make the listing and decompiler font bigger here. All right, now you get to watch me go through tool options. Give me just 1 second. How's that font size for the decompiler? Good. Okay. I'll change the listing view to the same font size. Give me 1 moment. Okay, we are back. Hopefully, folks should be able to see that a bit better now. Let me know if you're still having trouble. Can't do anything about the UI, I think, right now, but this should be visible now. Okay, so this is now the the pre-built binaries I provided for this workshop. They're the completely finished version of the downloader. So they include not only the download functionality, but also the write it to a temporary directory and run the shell script functionality. But the beginning of this is the same. And I've put up the unstripped version here just so you can look at some just for illustrative purposes. So you can look at what's going on a bit easier here. And I think I want to as well. I know some people are like, no, I will never read the decompiler output. I only look at assembly, no F5. But just to make things easy, we are going to look at the decompiler output. So if we go and look at where that request is being made, we can see, hey, this is a real function call, request blocking get. And there is this F statement here. And this is what our match, right? What our match keyword with like the funky syntax and the match arms eventually compiles down to, right? So Rust is meant to be, or tries to make the promise of having very little overhead and having what are called, this is like a meme by now, zero cost abstractions, right? Where you can write things in a fairly high level manner, but they compile down to something that's fairly optimized and the same as if you had written it all by hand in assembly. So in this case, all of this here is handling the state where the request failed. And that request failure is represented by this variable right here. This ends up being, this is actually the tag part of our tagged union. So again, the union itself contains some information about what it is. And if it's free, which in this case is just indicating, hey, the thing that's inside here is an error rather than the result, then we do all of this other business. You can see here, Ghidra is smart and it notices, wow, there is a function here that does not return. We will never get out of here. And that is the core panic format function here, which actually is responsible for creating that panic string and doing the cleanup the panic does, and eventually actually exiting the program. If you're an IDA, IDA will mark this function if you actually go inside it as no return as well. And the rest of this is just continuing on with the other case where, yes, our request is successful. And because this is the completed version of the program, there's a bunch of other stuff here. All right. So I'm going to go into my speaker notes here. So we can actually look inside this, right? So during the break, Alex asked me, like we have the panic bang there, and I explained, and what does the exclamation mark mean? And I explained that was a macro and not a real function call. Well, this is the actual real function call that lies underneath that macro, this core panicking panic format here. And if we actually go into here, you can see that there's some data that gets initialized here. And this is all part of the same struct, but I haven't defined it. So Ghidra is thinking that, oh, these are all completely different variables. And then this gets passed into something called Rust begin unwind, which does all of the actual backtrace stuff if you specified that environment variable and does the formatting and prints things out, etc. All right. So let's go and actually look at, because we can, right? We can actually go and look at the source code for core panicking panic format. Right. So let me just go back to our slide here. This was the Ghidra decompilation. Okay, this slide is titled "Looking into the Guts of Panic." which is a very strong title. Before we go to GitHub here, I am just going to switch my machine over to light mode because GitHub is going to follow, whether because I don't want GitHub to be in a dark theme because it's harder to see on the projector. So just give me one moment. Okay, we turn on the lights here. All right, and hopefully now GitHub should be happier. Yeah, okay, this is a bit easier to see. Awesome. Okay, and okay. So the stuff that I have on the slide is basically this source code that's inside, again, the main Rust-Lang Rust repository. We're at the 1.771 tag, so this is the version that we're all using on our machines. Then this is the exact line where that is defined. So I'm going to zoom in a little bit here. And like don't panic, like this is a lot more Rust source code than we've been seeing. Everything might look confusing if you've ever read Rust. It will be okay. Because there's only a few features here that we really care about. One of them is just what this takes as an argument. It takes a formatting object, which basically just contains all of the string arguments that were passed to this for it to format and eventually print. And here we have something called panic info internal constructor. So this is actually, if you actually go into here and if you look at this, this is actually what ends up being this thing right here, where we're initializing some data. So that basically that panic info internal constructor got inlined here. If we go back to our slide, I might be able to go to it on GitHub if we can use the code search. Maybe, well, I can't because I'm not logged in. Okay, we'll use the slide as a backup. All right. Yeah, okay. And there's also some other things here that only apply if you have certain features turned on. So this is another thing that you can do is you can say instead of like exiting immediately, or instead of exiting and doing some cleanup, please just exit immediately. Like don't unwind. Don't do any destructor calling, immediately abort. So this is something that the programmer can configure. I think that will remove some of the metadata from the binary, but not all. But that is something you could do as well here. But in this case, that's not present in our program, so that's not turned on. So. And then eventually we have the dreaded unsafe block. Oh, well, you might have heard about, well, Rust isn't really safe because you can use the unsafe keyword. In some cases, you will need to, I won't explain all of unsafe here, but you'll usually see this in cases where the program needs to interact with some underlying OS component, or it needs to cross some sort of FFI boundary. So if it's making a call to some C code. Of course, as reversers, you will never, like, there's no real consequence of like having safe versus unsafe in the binaries that we're looking at. That's really purely on the source code side. Okay, so I think I will need to find the documentation for this eventually. But let's see. Okay, so we're actually going to go and look at the documentation for panic info internal constructor. And like figure out, okay, what even is this? So here's Ghidra. I want to go back to my slide here. Okay, so I'm gonna show you a website called stdrs.dev. Now, this is, yes. Okay. Yes. So the question was from YouTube, and the question was, can we strip this metadata and this code from the Rust binary? Yes, you can. Part of what you can do is you can say to strip the panic unwinding code, you can do the panic immediate abort feature. That won't remove all of the panic metadata. There's a great project called min-sized Rust, which actually contains information on how exactly to strip it. I will go to that GitHub repository right now, just on the screen, and show you. Yeah, so all of this stuff is documented elsewhere, but somebody has gone and very helpfully collected all the information about how to remove everything from your binary. So it tells you how to strip. It's like right here. This is size optimization, LTO, if you want to make things really small, if you want to use a different allocator. But here is what we start caring about, which is abort on panic. So again, it's very easy. You can simply edit your profile.release section here, just like we did with the strip, and say panic equals abort. If you want to remove all location details, though, you will have to use an unstable flag, which is only available as part of nightly builds of Cargo. But again, this is also actually fairly easy. Like you can, Cargo actually just lets you use select like whether you use the nightly toolchain or the stable toolchain. So you can actually just do this and strip out that information from your binary as well. And yes, by default, Rust includes file line and column information from panic. I think there might be another thing in here. Yes, and there's also the panic string formatting code, which again, this explains here, even if you do panic equals abort, there's still going to be some of those error message strings by default. Again, there is an unstable feature in the Rust, in the nightly version of the Rust compiler, which you can turn on like so. So this is min-sized Rust. I know, I think Memnops said, Memnops, shout out to you if you're out there. I think Memnops said he was watching the stream. So Memnops is a really great Rust offensive tooling developer. And I think in all of his projects, he has a fairly sane, like, cargo.toml file, uh, which has all of those defaults on. Uh, Oh my God, he's writing a hypervisor now. Awesome. Okay. Uh, I think it was Arsenal RS that I was looking at, and there's a bunch of stuff here. Ooh, Mimikatz. Okay, let's pick that. Just pick a cargo.toml here. Uh, and yeah, so he has panic equals abort and LTO and the optimizing for size turned on. So I think there's I've seen some people just like copy his configuration. He doesn't quite have the nightly like strip everything on here, but I think you can't do that solely from the cargo.toml file. But yeah, I would recommend looking at Manovs's stuff, and I would also recommend looking at that min-sized Rust repository, which you can just Google. That's how I got there. So, great question. All right. So it's maybe a good time to pause. It's 11:05. We have about another hour left here. So we'll maybe take a 10-minute break and come back at 11:15. Go to the bathroom, get a drink, get coffee, whatever. We'll be back at 11:15. And I am just gonna lock my screen for a second here. I think you'll see that on a live stream as well, because I am going to the bathroom. Goodbye. Be back at 11:15. All right, everyone. It is 11:15 a.m., so let us regather. If you're on the live stream, I think my computer should be unlocked and you should be able to see things again. And let me just check here. Cool. Okay, so we are going to start again. All right, so where we left off, we took a look briefly at Ghidra into our binary. We found the place where we implemented the panic that we added, and we took a look briefly at the function that actually underpins that panic macro, which is core panicking panic format. Now, let's go and take a look at the documentation for panic format. It is documented on the main Rust standard library documentation site, doc.rustline.org. Now, this is kind of an unstable API. It's kind of part of the guts, part of the internals of Rust, but it's documented here well, technically it's not part of the standard library, it's part of the core library, but it's documented here on the site. In general, if you are looking for Rust documentation, it is basically all hosted online. It's going to look kind of like this. You can do search, etc. So you can actually see like, oh, this is the underlying implementation of core's panic macro. If nothing is used, if no formatting is used, and there's a bunch of other things that underpin panic as well. So if you've ever looked, though, at the Rust standard library documentation site as a reverser, one moment, just going to hide Zoom here. Yeah. More. Okay. Okay. That's better. If you've ever looked at oh my God, how do you guys know how to completely hide the Zoom like controls window? Okay, I'm just gonna move it to this screen, and then I think that's gonna be better. All right. So if you've ever looked at the standard library documentation as a reverser, so if we go to like std rust docs here just in Google, right? Like you go here, this is a standard library. You go and search string, right? Like, oh my God, std string. You might have noticed that a lot of times it just says private fields. You can't look in here because we're real developers and we don't depend on undocumented, unstable APIs or reversers. So we want to know like how this is actually implemented under the hood. So I will show you another website because we're going to look at some Rust internals. So this struct, which has the type core panic location, this is the actual metadata struct that holds our file name, our line number, and our column number that we saw when we invoked the panic and when that panic message was printed in our case. So if you actually go and search for this on the Rust standard library documentation site, let's go here. Let's go here, back to our string here. If you go here, right? This also says, it's private fields. Oh no. So you can see like the structure is created by a panic info location, which is one of the functions that was called inside our panic for function, but you can't actually see any of the internal fields. So there's this other website called stdrs.dev, which hosts a version of the documentation that just has like a flag checked when they're building the documentation to show you all the internal fields and to show you as well some other functions that aren't even like present in the regular docs. So if we actually go there, we can see exactly how a core panic location is defined. So this is a Rust struct. It's kind of the same concept as a C struct. It's some collection of data. There's some fields in it. The fields each have their own types. In this case, we have one type, which is a file, which is a string reference, which we'll get to. You could ignore, by the way, the tick A here for now. Those have to do with lifetimes, and we don't care about them as reversers because that's really just for programmers to enforce memory safety, and it makes reading things more confusing. So you can ignore this for now. There's a line there, a line number there as well. This is an unsigned 32-bit integer, a U32. It's pretty straightforward to remember. And a column number here, which is also an unsigned 32-bit integer. So this is useful. It lets us look at internal fields, right? But you do have to be cautious here because you might be like, well, I should be able to look into my binary and, there should be a string, and then right after there should be 4 bytes, and then right after, and that should be the line, and right after there should be 4 bytes. Well, if you've ever reversed a C program, the compiler can insert padding, it can change layouts, right? And in Rust, that applies as well. Type layouts in compiled Rust binaries are not stable. Right? You can't assume that things will be laid out exactly in the order that they have here. You can't assume that things are going to have padding or not going to have padding. It is up to you to examine the data in your particular binary and determine what the layout of this in your particular binary is. Now, with that said, though, we have this metadata struct, and we can actually find this metadata struct inside our binary. It's embedded in there. That's where all of that line number information and stuff comes from, right? There is one other step we will need to do, though, before we can fully understand the metadata struct, and that's knowing about the type layout of this like funny answer string reference thing in memory. Remember, right, we had three things as part of the definition for this. We had 3 fields. We had the file string, a line number, and a column number. These are pretty easy to understand, but what is this, right? So this is one of the most primitive Rust types. This is a technically called a string slice reference, but it's really a pointer to some constant string somewhere. You can kind of think of this as the the equivalent of like a const char, right? A const char pointer rather, in C, in your C binary. So there's documentation, of course, for it on the Rust Standard Library site. There's also a really great website called cheats.rs, which is a single page cheat sheet for Rust concepts, and it includes a really great section, which I've shamelessly stolen from, on the layout of some of these things in memory. And as with many other programming languages, this is not going to be just some pointer to some null terminated data. It's actually what's commonly referred to as a fat pointer or a pointer with additional metadata, right? So there's going to be a pointer, which is the actual address, and the length of the thing that this is pointing to. There's additional semantics to this as well, where like this is the thing that it's pointing to. The data here is expected to be valid UTF-8. That's enforced across the board, but we don't care as much about that as reversers. So that's the last bit we need to know here. We can actually put this all together and find this metadata struct inside our binary. And using the definition that we now know for core panic location here, which is very tiny, and using definition that we now know for how this constant string slice reference is laid out, we can go and actually make sense of where it is in our binary. So let's go back to Ghidra here. Oh God, where's my VM? And if we go one step back here, so you can see that this core panicking panic format, Ghidra has analyzed it and determined, hey, there's an argument here that's pointing to some other location in memory that Ghidra has already named for some reason. So if we go there, and I'll open this up here, Ghidra has named this S source main RS blah because it's determined that this is actually a pointer to a string somewhere in memory, right? So if we actually go there, right, we can see literally like the character source/main.rs here. And of course, this is not null terminated because if you look at the bytes here, this is immediately followed by some other string that's just there, right? There's no 00 byte there. And we go back here to the pointer. Okay, so if we keep looking at the bytes here past this, so this all is a pointer. If we keep looking at the bytes here, you can see that there's these 8 bytes here, which start with, I believe that's 0b. And that's actually just the length of source main.rs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so that should be, I think this should be 11 bytes long, unless I can't count, which is 0x0b right here. And all of this is a single 64-bit little endian integer. So all of this is our length. This is our pointer. This is our length. Both of these combined are our fat pointer, which is our answer, which is our string slice reference. Now, if you keep looking here, there's some more data here, right? Recall that we expect there to be another unsigned 32-bit integer somewhere, and another unsigned, that's the line number, and another unsigned 32-bit integer somewhere else, that's the column number. So in this case, in this binary, they're just laid out like exactly the way that it was in the Rust definition of the core panic location struct. This 0x1c here is actually a line number, and this 0x0d here is a column number. Now, because this version of the binary is like a later version that has like more lines of code in it, and some of this code got moved down, 0x1c is greater than, I think, what was our line number, like 8 or something. So that's different. But if you can find this in the binary that you just built, it should be the line number and column number that you saw when you invoked that panic. So that's where it is. That's a very useful piece of metadata because, and that's maybe why somebody was asking how to strip it out, right? Because you can actually use this to gather quite a lot of information, not only about like the main.rs, which we wrote, but also about all the places in the third-party libraries and in the standard libraries where those panics occur. So if we just like scroll through, like maybe in some other places here, you can see that there's quite a lot of these panic structs all over the place. And I haven't defined that struct in Ghidra or anything. I haven't like retyped this properly. But even if you scroll through, you can kind of see the shape of them, right? There's a pointer, there's some length, these 8 bytes here, there's these 4 bytes here, which are some small integer. There's another 4 bytes here, which are some other small integer. And scrolling through to see if I can find one that's just part of the standard library somewhere. Maybe a path. Give me a path. Yeah, I think this is another one. Yeah, so this is a case where this is actually something from a third-party library. So you can see that there's a cargo path there, plus like, here, I'll make this bigger. Yeah. Oh my God, this path is so long. Peter can't deal with this. So this is something from a library called H2, 0.4.3, and there's the source file right here as well. And I don't even know where this is. Can I expand this further? I think I've completely lost my UI element here. But this is a source file inside the H2 library, and you can view it here. It's from flow control.rs. Okay, that makes more sense. So if we actually go back here and look at the pointer that's pointing to this, this entire string is OX6A bytes long. This is a line number at 0x8b, and this is a call number. So because all of these Rust libraries are open source, we can go to like github.com/whatever/h2, and we can find that source file tagged at version, and we can find this line number, and we can find this column number, and we can figure out what the code that's pointing to this is actually doing. Because if we go back to what the xref is here, right, to whatever is like actually using this panic metadata structure. And again, this is an unstripped version of the binary, just to make things a bit more clear. Will Ghidra do this? Even if this is stripped, if you have that line and column number information, from there, you can figure out that this is H2 proto streams flow control send data, because that line number is going to be there. Sometimes like things will get inline, things will get moved around, so it's not going to be that exact location, but that's very helpful in cases where you don't have the symbols for your binary. All right, so that's another step beyond strings. And if you would like to know more details about this, I wrote a blog post about this. And if you like forget everything, you can refer to this blog post, and it describes everything and all the code and stuff in detail. I wrote a binary ninja script as well that extracts all this information. So you have this cool like, oh my God, like this part is library std source windows stdio.rs line 125 column 33. This is a shout out to, this is a plea for help. If somebody can write an IDA plugin that does this, or a Ghidra plugin, you know, free ideas. All right, so now, of course, there are limits on this. I predicted the question of like, how do you strip this? This is how you strip it. And the min-size Rust repository contains this as well. Most Rust malware that we're seeing, even if they strip the symbol information, which is trivial, they still have this information intact. I think probably some people will figure out how to do this. It's not hard either. It's just like maybe another extra step. But in general, I think this is a good example of how understanding the language a little bit helps us as reversers, right? Because before I realized what this was, I would see people be like, oh, wow, there's all these paths in Rust binaries for some reason. Well, let's just extract the paths and done, right? But if you actually look a little bit deeper, there's a line number information there, which actually turns out to be quite useful. And I figured this out by looking at the source code of the Rust standard library around that location. So even if like in the future people realize, right, malware developers realize that this is a trick that we can use, there may be other things that we can discover just by reading about the language a little bit and reading about the standard library a little bit. That's going to help us. So I think that's a good example. Okay, so we have half an hour left. Now it's time for exercise B, finding the entry point of the binary. So we had our easy mode unstripped binary. We're now going to go over to our hard mode stripped binary. All right, so now here is a giant diagram that says a quick look at the runtime initialization. So I'm not going to go through like all of this in detail. And also I have a light mode version of this diagram because nobody is going to be able to see that dark mode one. But I'll go over to Ghidra first, right? So in this case, I've already like found the entry point of this binary and we looked at main and so on. But I'm just going to open up the stripped version of this now. Oh, I think it's because I already had it open at some point. Unstripped. Stripped. Cool. So I've got the stripped version of the binary open here at the entry point of the binary, which is pretty much where Ghidra or Ida or Binja are going to take you to when you open a Rust binary, right? It's going to be libc start main, right? And if you like go into here, you're like, oh my God, what's happening here? Where's like my actual main function? Right? If you go into here, you're like, well, where is everything? What's happening here? Is this my main function? If you go into here, you look and there's some stuff here. You're like, oh my God, it's doing something with dev null. Right? And you're like, okay, well, clearly this malware is doing something with dev null, and you keep looking in here and there's nothing that looks like actual logic. Right. So this is something that people who are reversing Rust for the first time get confused on as well, is because most disassemblers and decompilers that exist right now don't really know about the Rust runtime, they can't help you find the real entry point of the binary that the programmer wrote. So all of the stuff that I'm showing here right now is part of like the Rust standard libraries, like initialization code. So you don't want to spend like your precious valuable reversing time reversing this, right? You want to be able to find, well, where is the real main code. So how does this work on like an abstract higher level? Well, that's what this diagram is for. If I can show it. Okay, cool. This is just a zoomed in light mode version of that diagram on the slide. But the way Rust binaries are right now on desktop operating systems, so on Linux, on Mac OS, on Windows, is that they still depend on the Platform C runtime library. So you're still going to see this C like runtime library shim before all of the Rust code. And that's where your decompiler is going to take you to when you open up that binary. So this is an example just for Linux and for libc on Linux. So you have start, you have libc start main, and then you have your familiar int main, argc, argv, mfp, and in a C binary, you would be able to go into like this main function and see all of the logic. But not for Rust, because that immediately takes you to the Rust runtime. So people say like, oh well, but Rust doesn't really have a runtime. It's meant to be like high performance and low overhead. Well, even the C programming language has a runtime. Even fairly minimal systems programming languages like this have a runtime because there is some initialization that has to happen for like a programmer's main to actually run. Unless you're doing like hardcore embedded systems stuff, there is still going to be some code here. Um, so I won't go into like the full details of this, but generally the entry point for like where all the Rust stuff starts is a function called stdrt lang start. This is a special function. It's annotated with a special attribute here, indicating this is the first part where we're going to start executing Rust code. So we've transitioned from the C realm to the left over to here. And you'll see that lang start takes 4 arguments. One of them is this main argument right here. Again, the types are after, and this is the type of that main argument. What all this means, this fn bracket and then arrow t, is that main is expected to be a function pointer that returns something of some type, right? And then we have the familiar argc and argv, which are passed on from our like C, argc, and argv into Rust land. So this is really the important thing here, because this main function pointer, that's actually the pointer to like the programmer's main, the one that we wrote. There's a couple of the functions that this goes through and calls, such as langstart internal, because langstart just calls langstart internal. It doesn't really do anything. There's also a runtime initialization function here and some potential panics. So the default panic error code, if because there's some cases here where some parts of the initialization can fail, and you do want to like handle that gracefully. So there's a panic case here. The default panic error code is 101. If you ever see that, that generally means a panic during the runtime initialization somewhere. But this, because we're lazy and we want shortcuts, this is actually this little bit of code right here is part of the implementation of this initialization function, this stdrt init. And what this does is one of the most important initialization steps that the Rust runtime code sets up. It creates a new thread because you need a thread for things to run in, right? And that new thread by default across all platforms is called main. And there's a nice new string there, little string there that, gives it its name. So shout out to my colleague Ken for teaching me this, because I had like a way more convoluted solution for finding main before this. And he was like, well, there's a string there. So if we go back into our binary, right in Ghidra, we can find that main string. And we can use that to kind of it won't lead us completely directly to the main function of our code, to the main programmer code, but it will help us orient ourselves as to where we are in all of this junk, right? So if you run strings, you're going to see a string that looks something like this. It may or may not be stuck together, with a bunch of other strings. But there's going to be a string there that pretty clearly says main. And that's the equivalent to the code that it just showed here. That's this being set up here. So now that we've oriented ourselves here, once you see this, you start realizing, okay, actually, this is all part of the runtime initialization code, right? Like before this point, we haven't even set up like the main thread for our main Rust code to run in, right? So it can't be the programmer's Rust code, unless shout out to Nordgren, who made a CTF challenge where he bypassed all of this and used a Windows exception handler. But that's an exception. Please never write malware, Nordgren. I'm begging you. So this right here is part of the initialization code. So we know that our actual like programmer code has to be somewhere after this. And I'm going to give you a little spoiler here. It's actually this call right here. This is like maybe a little bit confusing to read in the decompilation view. but it's maybe a little bit clearer here. So this is a call to whatever RBX plus 28 is pointing to. So this is a indirect call to somewhere, right? And the address of that is, somewhere in like all of this stuff to happen before. So one pattern that you'll see often, I won't go through like the nitty-gritty details of like, okay, well, let's trace back that bit of data to like exactly where it came from. But one pattern you'll see often is that you'll have some variable that's set up right before this like main before this runtime initialization call, and that variable will be pointing to some function which is somewhere in the binary. This won't happen for every binary, right? It's kind of up to the compiler and how it decides to optimize things. But very often that function will actually be the real main function of your binary. And here's our URL right here. And if we go back to the unstroked version of that binary, and we go back and to here, maybe. Yeah, we can actually see the version of this that has symbols. So you can see that this is the C main right here. And this variable is a function pointer to a simple downloader main. This is our line start internal, which we saw in that diagram. And one of the things that it takes as a parameter is this simple downloader main function pointer, exactly as it was in the source code. Well, kind of pretty similar to as it was in the Rust runtime initialization source code. Okay, so let's go back. Dark diagram. Okay, so this is like what that looks like in the actual runtime initialization source code. Again, it's open source. You can go and look at it. You can go and figure this out yourself if you know how to read a little bit of Rust. This is line start internal. This is init, where we have our C string new main. And this is, what is this? Oh yeah, this is some of the Unix mod.rs, which was like that giant function we were looking at with like the dev nulls and stuff. This is what it actually looks like inside. And this is my spoiler for, okay, this is where your programmer main is. By the way, that trick with the main string works for Windows binaries as well. I don't think I linked this diagram, but oh my God. The table has just collapsed because I kicked the leg. One moment. Yeah. Oh, okay. Yeah. Okay. I won't kick it. Thank you. Okay, we're good. So I have a diagram on my Mastodon account somewhere, which illustrates this for Windows binaries as well. With Windows binaries, there's a few other landmarks you can also use. I think there's import of add vectored exception handler, which is somewhere in the initialization code. But the point is, if you go and actually look inside like the open source, right, runtime initialization source code, you can find some more landmarks that you can use when you're reversing your binary. Okay. I think we have 15 minutes left, so I am not going to go through writing the shell script running functionality in detail, because I thought I paced myself properly, but I clearly did not. However, this code is available on GitHub. This version of the code that I have on the slide is what's in that GitHub repository. I will kind of go through this on a higher level. So in here, we've added a few things, right? So now we want to actually do things with our response. And one second. Okay, so now we actually want to do things with our response. Recall that when we ran the initial version of our downloader, we just had like headers and like metadata, right? We didn't actually like look inside that response object. For the text of the response, we didn't actually like write it to disk. We didn't actually run the shell script in any way. So now we're actually going to look inside it. I'm going to open up the the VM again, and I'm just going to open up the pre-built or like the folder that has the pre-cooked code inside it. Which is, if you're looking in your VM, it will be in Home Rest Reversing Workshop 2024 and in the simple downloader folder. So I'm just going to open this in code. Okay, so this is the full code here. There's a couple of things you might kind of immediately realize here. One thing is that I've barely annotated like any types here, right? You can write this in a fairly high level way. Another thing here is that this has very little that's platform specific. So again, if you're on Windows, right, you can you can't run the shell script, but you can download the executable version of the Rust up installer. And actually a lot of the code here is exactly the same, right? Rather than using bin sh on Windows, you can use command.exe to run your binary, or you can actually just pass the path of your binary directly in here. And the rest of the code is exactly the same, right? There's very good standard library facilities for providing a temporary directory, for example, and that will just work and give you /temp on Unix and give you like C local app data temp, blah, blah, blah on Windows. std process command new will just work. It will do the necessary exec VE things on Unix and the surreal horror of process initialization on Windows. That you don't have to think about that, right? So the standard libraries facilities are quite good in letting you write these things in a cross-platform way. And actually, most third-party libraries are going to use the standard library facilities under the hood as well. So this kind of explains why there's some ransomware groups that target both ESXi servers, which are Linux, and Windows machines, right? And it kind of explains to some extent why they decided to rewrite their things in Rust, like with Hive Spider and Hive ransomware. It's because you can have like one code base, right? That covers both of these operating system cases. And again, with the DPRK actor writing things for Mac OS, it's fairly easy to do so. So let's actually go and run this. So again, we can go into our terminal here. I'm going to open a new tab here. And we'll go a few directories up to our pre-built code. And we can literally just do cargo run -- release. And, stuff is going to compile. It's going to take a bit. But once this compiles, should immediately run. Boom. Okay. So recall that this is going to download and run a shell script. I think I still left the debug print of the headers here, but this is that download. And then there's another message here that just says output of running the payload, which is the Rust installer, which is a totally benign payload. If you want to repurpose this for your cool malware downloader, feel free to do so with this program because it will just work. And as part of this as well, we wrote something to, we dropped the shell script to our temporary directory here. Now this is documented and it does tell you like where it actually puts stuff. Windows, it uses get temp path. Unix, it just uses /temp. So we can actually go and look in /temp as well, and we should be able to see our shell script there. I think it's called payload.sh, is what, or just payload. So it's right there. And you can cat it as well if you want. But this is the Rust-up installer shell script. Okay, so we have successfully run this finally. Now, we encountered our one string type, right? Our static string slice that's just embedded inside the binary. But usually, like, the interesting strings that in the binary are going to be constructed at runtime, right? Otherwise, our program would not be able to do anything interesting or dynamic at runtime. So if you actually look at the type of this response text right here, which through like unwrapping and like opening up that response object and taking out the text is actually going to be the contents of the shell script that we downloaded. Is actually going to be the contents of the HTTP response. This is of type string with a capital. So this is the Rust standard library string type. This is not a primitive type that's just kind of in the language. It's part of the standard library. You can have alternate standard library implementations with like crazy strings, but most Rust binaries that you'll see will use the standard library. Now, of course, since this is a dynamically growable string, and because we also like in Rust, there's a lot of fat pointers with metadata. This is also just a pointer with metadata attached to it. So you have a pointer that's pointing to some string data that's somewhere in dynamically allocated memory, right, in your program. And attached to it is capacity plus the current length. So if you're familiar with like std vector from C++, this might look very familiar to you, or if you've ever implemented any container type, this is like bread and butter stuff, right? You have the total capacity that you've allocated and the current length of whatever's inside. And of course, this is documented, and there is a cheat sheet as well that tells you about this. So this is a meme I really like. I mean, I'm not like a big fan of the gender binary in general, but I think this is very illustrative, because a lot of C programmers and a lot of reversers as well will just tend to see like strings or like blobs of data as like pointer and like that's it. In Rust, there's actually quite a number of different types of strings. We covered string and answer, but there's also all sorts of other string-like things, like a vector of bytes that can happen to be a string, or an OS string, which is just whatever the operating system thinks is a string. So UTF-16 for Windows, right? On the reverser level, we might be, we're going to look at a lot of these things as just pointers with some potential metadata on top of it. This is another example here. If you actually look at what std process command expects for what you pass into it, this is expected to be an OS string. Right? Because this is a string that your operating system needs to understand. In this case, I just passed a string literal here, bin.sh, and through some magic, the SD process command new is going to turn that into an OS string, but really under the hood, this is a slightly different type of string. So it's still a pointer with some length on it, but the data it holds is different. Yeah, this is, I don't think we have time for this. Basically, everything is a pointer plus length. If you have any kind of dynamically sized structure in general, whether that's just an array of bytes, a vector of bytes, an array of pointers, etc. I don't think we have time for this. We really don't have time for this very brief introduction to how the Rust compiler works. I will talk about this a little bit since we are actually almost at the end. So you might have heard like, well, everything that Rust does is just LLVM, and also Go is also LLVM, so therefore they're the same. And that's not quite true. There's so Rust does depend on LLVM for the very lowest level of generating machine code, right? But there's actually a lot of things that the Rust compiler does before that. Some of it is stuff like that's for memory safety, right? Like for borrow checking. But there's also several intermediate representations that the Rust compiler uses that aren't necessarily going to reflect, what you see at the Rust source level. Um, so, and with other languages that use LLVM, all of this stuff before the LLVM IR layer is going to look like very different, right? They might layer their own runtimes on top of it. They have their own optimizations that they do before the LLVM level, right? They don't depend generally on LLVM to do all the optimization. I have another diagram here, but I don't think we have time for this. So this just illustrates how we get from that OS string, which is defined at the Rust source level, to the actual assembly that we see. So I was going to introduce a bit about the Rust medium level representation here. I'll just zoom in and do that very briefly. So this is our bin sh here. It's an OS string. The Rust compiler will do some stuff. This stuff can change between compiler versions. Remember, every 6 weeks, right? You have a potential change to everything. This is going to get turned into some medium level representation where actually that OS string gets split apart into something internal to the Rust compiler called a scalar pair. Which is, again, just a fat pointer, right? It's just a pointer, again, plus an integer, which is the length. Again, there's a pattern here. And there's some other metadata here as well about that instructs eventually the part that converts to the LLVM IR about how this should be laid out. The Rust compiler does more stuff, which can change between compiler versions from this MIR to LLVM IR, which it emits, right? So all of this stuff before the LLVM IR is the Rust compiler deciding where to arrange things, how to split things, what the representations of objects should look like at a fairly granular level, right? Including some layout details. And finally, the LLVM turns this IR into actual x86 64 assembly. So I don't really know that much about LLVM. I put fairly stable with a question mark here because I think like this is fairly well defined at this point. You have a pointer, it has an alignment. This is the first argument. You have an I64. This should look fairly reasonable. But I don't actually know if this is stable or not. But it is going to be a lot more stable than the stuff that the Rust compiler is doing, which is every 6 weeks is going to look like. Now, there is, if we go back to this slide, this just tells you about how I got that nice like type layout thing. There's some magic you can use with the compiler to do it. This is everything is a fat pointer. This is my edited version of that meme. Developers see this, and reversers just see a Rust compiler scalar pair with a pointer plus integer. Yep, there's some other stuff you can do to inspect those type layouts in detail. I have another Binary Ninja plugin that covers some of this as well, where it actually turns some of these type layouts into things that look like C. Now, I do want to cover this as my last thing before we go, is Ghidra, when we saw the decompilation, was inferring some arguments, right? It was saying like, okay, there's something, if we go back to our VM, if we open up Ghidra again, it's saying, okay, I think stdrt, lang start internal, takes these arguments and they are in this order, right? And it tries to make like some it tries to analyze the binary and tries to determine, okay, well, what arguments are being passed to which functions. Of course, if you've done reversing for any significant amount of time, you might know that often you have to fix things, right? Like the decompiler isn't perfect. It doesn't realize that sometimes, okay, well, this register is actually used, or this struct that we're passing in is actually the size. So you often do have to fix arguments, right? For Rust, you might realize that you have to fix that sometimes even more. Because recall that if we look at this diagram here, like LLVM is going to be like, okay, we have like, we're on x86 64, we're on Linux, there's an ABI here. I have code that I can use to turn this into this. But the stuff that Rust emits as LLVM IR might change over time, right? So it might decide to lay these out differently. It might decide, okay, I'm going to just pass in one pointer here, and then like somehow you just have to realize that there's a length here, right? Like this, recall that the OS string was just one object, right? To the developer, it looks like just one argument. So in the future, the Rust compiler could decide, actually, I'm not going to split this anymore. I'm not going to split it across two arguments. You just get the pointer, and you just have to. And there's some other code inside the function that is like, oh, there is a length here. I will extract it, right? Without having that as a separate argument. And as well, this ABI that the Rust compiler uses isn't quite stable. I think technically the Rust compiler can also do whatever it wants with what registers are used or whether things are placed on the stack or in registers. So in Ghidra, they very recently added something called Rust call, where you'll see that Rust functions, or things that Ghidra thinks are Rust functions, are annotated with the Rust calling convention. That calling convention does not exist. That is something that is created by the Ghidra developers. If you look in the Ghidra source code, they have like an XML file where they define their version of Rust call. And only, I think they only do it right now for Unix x86 64, where they say like, okay, we think that this register is used and it's used to indicate this argument. And they apply that like statically across like all functions in Unix x86 64 binaries that Ghidra is analyzing. But this can change. The Rust compiler can change. This is going to look different for different platforms. And there's going to be times when the decompilation is incorrect and where you have to define the calling convention yourself. And again, there is no stable Rust ABI, right? You might be familiar with Golang, and Golang having they used to have, I think, a stack-based ABI, and now they pass arguments in registers, and they had like this whole version change, and they were like, okay, new programs after Go 1 point whatever are using the new ABI, and Go to Go code is going to use these registers, and it's going to be perfect and beautiful. Rust doesn't have that stability. It does not guarantee anything for you. You might see certain registers being used more in the program, right? And it might kind of look like C, but that can change at any point. This is the diagram I just showed. One last thing, if you are really confused and dismayed and there are no symbols and you forgot all of this and you can't do anything, a lot of programs do just use the OS APIs under the hood because the Rust standard library just uses the OS APIs under the hood. So what you can always do is you can find, oh my God, this is an imported write function. This is like write to, right? And it's just a Linux write API. And you find it, you clutch onto this for dear life, and you work your way back up from this. So this isn't a great solution because often these OS functions will be nested quite deep inside the standard library. But in some cases, like with, if you see like a Windows import that's like very obviously, I don't know, like crypt API, whatever in it, then you can kind of trace back from that to the original functionality. Okay, I think that's it. That's the conclusion. What do we learn here? Hopefully some things, but I think the general themes here are a centralized open source, well-documented standard library and compiler makes it easier for us to go and look at source code and go and look at implementations and go and look at what's going on under the hood, right? Second of all, like we wrote that initial downloader functionality in like, I don't know, like 10 minutes, 20 minutes. And you can like if you learn a little bit about Rust syntax, you can write the rest of that in like an hour, right? But that's the binary that produces is like terrible for reversers currently. So this is something that I'm worried about, is that the asymmetry here is quite large. Like there's significant investments by large companies in the Rust ecosystem, in improving the compiler, in improving libraries, in improving the standard libraries. There's like armies of people working on the compiler side. Malware authors can use that effort, but for reversers, it's like, oh, here's my presentation. Like, I don't know, there's no tools, have fun. Right. So uh I don't know what the solution is, but I think some of it is going to have to be automated. So again, shout out to NoFix. So he's actually built a tool called Rust Bin Sign, which tries to build those libraries and build IDA flirt signatures for those libraries. And he's actually got pre-built flirt signatures for a lot of those standard library functionality, which is also going to really help with those stripped binaries. So if you go there into this repository, into the Windows directory, these are standard library signatures for I think almost every version of Rust until 5 months ago. So the point is, though, that he did this automatically, right? This was he had to write a tool to do this, and I'm still having some trouble with this tool. So no fix if you're out there, I might need to ask you some questions for support. But I think the solution is going to have to be automatic generation of signatures in this way, automatic recovery of type layouts, because without automation, there's just no way that we're going to keep up with the rate of change of the Rust language. I want to thank everybody that I've ever discussed Rust reversing with, whether it's my colleagues or folks online, everybody who's sent me samples, who's looked at samples. A special thanks to the following people, you know who you are if you're out there: Johannes, Josh, Ken, Leland, Norgaren, and NoFix. That's all. You can find me on Mastodon at cxiao at infosec.exchange. I also have a website at cxiao.net where I've written a little bit about some of the Rust stuff. And this screaming gull is an accurate description of how we all feel when reversing a new programming language. Thank you very much, everyone. And I think we're over time, but I don't know if there's any more questions on the YouTube stream. Okay. Okay. Everyone is gone. They're all collapsed. Are there any questions here? Yes, I should be able to post the slides afterwards. Yeah. Which extension? Oh, in Obsidian. Yes. So the question is, what is the Obsidian extension I use to make the diagrams? That is actually a new built-in feature of Obsidian called Canvas. So you should be able to have it without any extension functionality. So just Obsidian command palette, new canvas. Shout out to Obsidian. Okay. All right. Well, if you have other questions afterwards, or if you just want to talk, come and find me during the rest of the conference. I'll be here for the rest of today. Thank you very much, everyone.